So in the last several segments, we covered selected topics in experiment design, hypothesis testing, and statistical estimation. And we motivated these topics by considering the so-called decline effect, where scientific results turn out to be less reproducible over time, or their effect size diminishes over time under repeated experiments. Okay, and we found that things like publication bias and the misapplication of statistical methods can explain a lot of this effect. Okay, and then we also talked about the Bayesian perspective, which allows you to incorporate prior knowledge easier, but opens the door to subjectivity leaking into the analysis, which is one of the reasons why it was largely rejected at the beginning of last century. But it's making a resurgence thanks to computational techniques that allow you to do sampling of complex distributions, at scale. And we didn't go into too much detail there, but I hope to get back to it before the end of the course. Okay. So in the next few segments, I want to talk about more of an algorithmic perspective that is more closely associated with the terms machine learning and data mining. Okay. So what is machine learning? So Pedro Domingo here at UW wrote a fantastic Communications of the ACM article in 2012 that gave an overview of machine learning. And what he said was that machine learning is systems that automatically learn programs from data. So what he means here is that when you write a program by hand, you're explicitly stating how to map a set of inputs to some desired output, right? You're giving a recipe for doing that. But the point is that given enough examples of inputs and desired outputs, you can infer the program that maps it as opposed to having to write it explicitly. So the joke is why bother writing programs when you can learn them instead? Okay. And maybe another view is teaching a computer about the world, but I perhaps prefer the first bullet here. Okay. So it's worth maybe a few minutes or just 1 minute or so talking about what the difference between statistics and machine learning is. It's probably not worth putting a lot of time into this or thought into this because, terms are not necessarily precise and they grew up in some historical context and reflect different cultures rather than being some well-defined notion that you can reason about. But there's a paper pretty long ago now, in 2001, that talked about a certain kind of difference, although they weren't specifically referring to machine learning. It captures what I believe to be the real salient difference here. Okay, and so the model here on the left is that everybody involved in the space is trying to do the following, which is, observe that nature is able to map inputs to outputs, and we want to be able to predict that, computationally. Okay. So the statisticians will attack this problem by, actually trying to model the world through some stochastic process. In the paper, they talk about data modeling. They talk about modeling the data. What they mean is modeling the process that gave rise to the data that you see. Okay, and so the idea is that once you have a model of the world, you can use it to sort of hypothetically draw more samples and reason about the entire population. Okay. But another view that's maybe this more algorithmic view is, look, we recognize that nature is difficult to model and we don't really care if we have an accurate model of it. All we're trying to do is measure our performance in predicting the outputs that we've seen from given inputs. Okay. So it's not important that the model that we produce, that the program that we generate actually reflects the real process that's going on in nature or not. We don't claim it does, but what we do claim is that it does a pretty good job making predictions anyway. Okay, and so I think this is the notion that's more associated with the machine learning approach. All right. So let me give you an example that comes from Witten that's used pretty ubiquitously to explain some of the concepts of machine learning. And we won't use this example too much, but it is useful for a variety of purposes. So imagine you're trying to predict when someone is going to play golf or play tennis or do some other outdoor activity. And we imagine that it's a function of the weather. And so we take in inputs like the outlook, whether it's sunny or overcast or rainy, the temperature, whether it's hot, cool, mild, the humidity, how windy it is, and we want to learn a function that takes in those inputs and produces a yes or no answer whether or not we play, say, golf. Okay, and so the simplest version of this you might do just intuitively is just try to predict it with a simple rule. So you might say, look, maybe we only play when it's sunny. Is this true or not? Well, no, it's not true, because we can find examples where we did indeed play when it was overcast. Okay, you might say, well, maybe we don't play if it's rainy and windy, and that turns out to be true, but there's also other times that we don't play as well. So the pattern that, if a function exists that can predict this output well, it's perhaps not something that we can express in just one simple rule, which is kind of the limit of what we can do, mentally just through intuition. And so the idea is we need some principled way of coming up with more complex models when they're needed. Okay. So fine. So some terminology. This problem is an example of a classification problem where there's a learned attribute and it's categorical. It can take two values in this case, 0 or 1. If the learned attribute is more of a numeric value, for example, what our score at golf was, as a function of the weather, if we want to try to predict that, that would be more of a regression case. Okay. And really not just learned attributes, probably when all the attributes are numeric, it becomes more of a classical regression case, although there's ways to handle this. And so we've talked about regression in terms of, fitting a curve to data, but when you use that fit curve to actually make predictions, that's when it's you can see that it's analogous to the classification problem over categorical data. Okay. So more terminology. The golf example we just gave is an example of supervised learning, where you're given examples of inputs and the desired outputs, and we're trying to learn the relationship between them. So we train a model to do this. And there's also a notion of unsupervised learning, which is you're not given any labels whatsoever. You're just given the data, and you're trying to understand the underlying structure in that data. Okay. So this is things like clustering algorithms or dimension reduction algorithms, if you've heard those terms before. So let me give you an example that can be sort of cast as either supervised learning or unsupervised learning, but it's instructive as an unsupervised learning case for right now. So imagine you're just given a big corpus of documents, and you're trying to figure out, you want to make a prediction of what topic a given document pertains to. And so, if you see the phrase, the Falcons trounced the Saints on Sunday, you might guess that this document is about sports, while if you see that the Mars rover discovered organic molecules on Sunday, you might guess that this document is about science. And so, how do you set this problem up as a machine learning problem? What are the rows and columns? We just had an example where there's sort of rows and columns, and we said for one record, we're trying to predict the output given the inputs. What are the rows and columns here? Well, this shouldn't be too bad, since you've seen this before in a couple of assignments now. Okay, so how do we set this up? Imagine you had 5 documents that were just represented by these simple phrases here. So document 1 is just the phrase Romeo and Juliet. Document 2 is Juliet, oh happy dagger. Document 3 is Romeo died by the dagger, and so on. Well, with some stemming and some normalization of the terms, we could associate a column of data with each one of these terms, and each document is in a row in this table or matrix, and we put a count in each position for the number of times that term appears in the documents. And again, you've seen this in a couple of different assignments now. Okay, so given this basic setup, you can think about a supervised learning version of the problem or an unsupervised learning problem in different contexts. So the supervised version is, you have a corpus of documents, and a human has assigned a label to each document in the corpus. Okay, and so you want to come up with some sort of model that can predict that label given the text in the document. Okay. An unsupervised learning version of this problem is that no labels are given, but you want to discover groups of similar documents. So you want to say that, look, all these things have something in common. We don't know, maybe we don't understand that it's about sports, but we know that they all have something in common. And these over here, maybe we don't know it's about science, but we know they all have something in common. Okay, and so that would be an unsupervised learning problem, in particular, sort of a clustering problem. All right, so in all these cases, there's going to be 3 core components to think about, and this, again, comes from Pedro's article. So they are representation, evaluation, and optimization. All right, and so every problem you come into is going to have something to say about all 3 of these. Okay. Representation is, what exactly is your classifier, right? Is it a rule like the ones we saw with the golf example, right? A simple hypothesis of maybe when it's sunny we always play golf, right? The space of all possible such hypotheses, all possible such rules, is the representation of this classifier. Okay. Or is it, or each one of those is perhaps a representation. Or, is it the space of all possible neural networks that map inputs to outputs, right? Or is it a decision tree, which we'll talk about in a little bit? Or if it's more numerical data, if you've got a 2D scatter plot and you try to draw a line that precisely separates the data such that all the positive examples are on one side of the line and all the negative examples are on another side of the line, the space of all possible such lines is the representation here. Okay. All right. So what are the nuts and bolts? What are the units that you're talking about? Okay, fine. So once you have that figured out, you can think about, well, look, how do I judge whether one particular example of this instance of this representation is effective or not? How do I know the good ones from the bad ones? So, for example, with the rules, when you're trying to play golf, I've got a rule that says when it's sunny we play golf and when it's rainy and windy we don't. Those are two different rules. How do I judge which one's better? Well, you have to make some sort of a choice about how you're going to evaluate this thing. And it could be just the number of errors it makes on some given test set, or you could define some notion of precision and recall, or if it's more of a regression numerical case, you could talk about the absolute error or the squared error or other variants, right? But you need to make some sort of a decision here. So now we have, if we have the representation, we have a space of possible units, and now we have a valuation method selected where we can take a given instance and determine whether it was any good or not. Fine. The third piece here is optimization. So how do you search among this potentially massive space of, or potentially infinite space of possible hypotheses? Okay. So in pretty much no case is it going to be feasible to enumerate all possible instances and apply your evaluation technique to find the best one. So you're going to have some method of searching through this efficiently. Okay. Now, what's useful, I think, about this breakdown is that it helps make sense of the various terms and methods you'll hear if you sort of scan the machine learning literature. Is that many times you'll be what will be being presented is just an optimization technique that can apply to a variety of different representations and even evaluations. And you can plug in your own evaluation, plug in your own representation, and it'll still work. Other times you're talking about a representation that is amenable to a variety of different optimization strategies or particular algorithms. Okay, so it helps to make sense to understand which one of these three things you're talking about, or if you're talking about something that really denotes some choice about all three. Okay. And so as we talk about methods, we'll try to refer back to these three components and describe what's going on in each case. Okay, let's consider some specific algorithmic techniques. Okay, one of the data sets I want to use to illustrate these techniques is the passenger list from the Titanic. And this is a data set that's available out there on the web and has been used for various purposes, but it's also available as a Kaggle competition, and it's one of the competitions you can participate in. It's used for getting started, for kind of a training exercise. Okay, so what this is a one record for each passenger on the Titanic, or in the training set, a subset, along with various attributes that describe that passenger and whether or not they survived the sinking of the ship. Okay, and so the columns here are survived, which are given as 0 or 1, 0 meaning they did not survive. And P class is the ship's class, like first class, second class, third class, which sort of deck they were on. Gender, age, SIB, SIB-SP is the number of siblings they had on the ship. PARCH is number of parents and children. So number of children if you're a parent, or if you're, well, actually either way. So total number of parents and children. Fare is the fare in dollars that they paid. Cabin is an indication of their cabin number, and you can see that there's a lot of missing values here where either wasn't known. And then embarked is a one-letter code indicating where they got on the ship. Okay. So fine. So the first thing to do probably whenever you're tackling these problems is to inspect the data, right? So if it's sort of telling you something, you shouldn't ignore it. And if, more importantly, if it's not telling you anything, that's maybe a sign that it's going to be tricky to sort of learn a pattern automatically. And so one thing to do is to start plotting scatter plots of these various columns. And so one idea you might have is, well, maybe women and children first, right? Maybe the kids tended to survive, so you can plot age. And then maybe you might imagine that people who had paid more for their fare sort of had more influence on the ship. And so this is a scatter plot of age versus fare, and you can see there's probably not too much of an obvious pattern. There does seem, oh, blue here, by the way, is survived, and red is did not survive. So you can see that there's kind of a cluster of blue around, you know, the very young children maybe tend to survive much, but other than that, there's not anything really obvious here, okay? Or at least it doesn't seem obvious to me. All right, another one you can do is age versus sex. And I played a little bit of a trick here where I'm plotting categorical data as a numeric attribute, which is a pretty useful trick to do. And you can see that this is also kind of smeared a little bit here. And what I did was add a little bit of a jitter so that you could see the values. Otherwise, you know, it's not that someone is sort of, you know, 0.1 male and 0.9 female or anything. It's just that if you don't add that jitter, then all the values end up directly on top of each other, and all you see is the last one plotted. And so if you spread them out a little bit, you can kind of get a sense of how many are red and how many are blue. Okay, and so one thing that does seem pretty obvious here is that, you know, the women and children first did sort of hold up, right? Certainly there's more blue here than there is in here, but again, the age doesn't necessarily tell you all that much. All right, so fine. So maybe, you know, a very naive classifier, just to sort of illustrate a starting point, is what's called the rote classifier. So this is, look, if I see a new record coming in, I'm going to go look for an exact match in the training set. And if I've got something that agrees on every single attribute, then I'm going to assign it to the same class. If I've seen this example before, then, you know, darn it, I know what to do. Okay. And if it doesn't, then you have to just guess. Okay, so this classifier is not particularly useful. So a minor improvement on this one is the following. You know, given a new passenger that we haven't seen before, see if it matches an existing example on some particular attribute. And if it does, then take a vote among people with the same value and see what they say, and use that to determine the class. So for example, you see a new passenger and you notice that it's female, then you can look back at all the other females you have, and if there's more females that survived than who did not survive, then you declare the new passenger must have survived as well. Okay. But, you know, there's lots of possible rules like this, one for every value of any attribute, and, you know, in particular, an attribute can have more than just two values, male and female. So you need some way of choosing among these. So we have the representation of the hypotheses in terms of rules, right? Each rule is a hypothesis. Okay, so that's the representation. Now we need the evaluation. How do we determine which ones are good and which ones aren't? Well, one thing you can do is construct a confusion matrix, which is a square matrix with a number of rows and columns for each unique label, each unique class label. And the diagonal of the confusion matrix will tell you which labels you got right. Okay, so for example here, using this one simple rule that looked pretty good when we drew the scatter plot, if sex equals female, then survive equals yes, otherwise no, we have 468 instances where we classified the passenger as having not survived, and indeed they had not survived. We have 233 cases where we classified them as having survived and they did indeed survive. And the other values are the mistakes that we made. We classified 109 as having survived who actually did not, and we classified 81 as not having survived who actually did. Okay. So this is actually useful for sort of visual inspection, but it doesn't really give you a single number that you need in order to actually, you know, build a program that would do this automatically. So what you can also do is just measure the accuracy, which is here, you know, 468 plus 233, the number we got right over the total number. covered by the rule. And in fact, we didn't have any missing values with male and female, so they're all covered by the rule. Is about 79% correct and 21% incorrect. So this is not too bad, given that it's such a simple model. Okay. Fine. So another scatter plot we could look at, maybe in an attempt to improve upon it, is look at the, whether they were in first class, second class, or third class. And here, we don't have sex on here, which is a pretty strong indicator, but we do see some interesting patterns. It looks like people in first class tended to survive more, certainly more than people in third class. And then it looks like the kids in second class tended to survive more than the adults in second class. Okay, so this suggests a slightly more complicated rule. Okay. But here's just another example of a simple rule just for class itself. If you're in first class, then you survive. If you're in second class, then you survive. But if you're in third class, then you don't. And so now, the confusion matrix we can build again. Remember, the confusion matrix is just the class label, so it's still just no and yes and no and yes. And how do we do here? Well, the diagonal tells us 372 plus 223 over the total number is only 67% correct. So it's a little bit worse. Okay, so we have a representation of hypotheses and we have an evaluation method, but we need some kind of a search strategy to consider all these rules. And so for the one rule case, you conceivably could just enumerate all of them. And so one potential search strategy, maybe I hesitate to call it optimization, is just to do so. So the one rule algorithm is this. For each attribute A and for each value of that attribute, create the rule. Count how often each class appears, find the most frequent class, and generate a rule if A equals V, then class equals C. Okay. And then you can calculate the error rate of that rule. Pick the attribute whose set of rules produce the lowest error rate overall. All right. And now you'll have one rule. Now, by the way, one rule, again, refers to actually an attribute. So it's an if then, if then, if then, if then, covering all the values of that attribute, not just, for male and female, that's not two rules, that's just one rule. Okay. So this is kind of an exhaustive search strategy for which to generate these rules. So how far can we go with this? Well, you can imagine having more complex rules with more conditions in them. And you can also imagine having a whole set of rules, and your classifier now becomes checking this whole set of rules to determine the class. Okay. So how do we go about building an appropriate set of rules to come up with a classifier? Well, so one approach is this sequential covering, which looks like this. You start off with a data set D, and you initialize the rule set R to be empty, and you say for each class, say survived or not survived, you can construct one rule that correctly classifies some instances in D, right? So you capture some of the people who survived, and does not incorrectly classify any of the other classes. Okay. Okay, and then you add that rule to the rule set and remove from D all the instances that were correctly classified by this rule. And so we're going to keep on adding up rules this way. Now, that's great, but it doesn't tell you how to actually find that next rule. And so that's what this explains. So come up with a set with an initial rule R that just trivially assigns a class value to every record. Okay. And so while it incorrectly classifies some of the non-C instances in D, so write R as the antecedent of R determines C. And so here the antecedent initially is nothing. Okay. And then for each attribute value pair A equals V, where A is one of the attributes and V is some value of that attribute, figure out the accuracy of that rule, just like females predict survival, and we determine the accuracy there with 79%, or male determines, well, we're just dealing with one class right now, so just survival. Fine. And then figure out the attribute value pair that has the maximum accuracy over D. Okay, and in case of a tie, choose the one that covers more cases. All right, so now update the rule R with this new condition, A star equals V star, and remove that attribute from consideration in the set A. Okay, and then keep going until you are no longer incorrectly classifying some of the non-C attribute instances of D. And now in the next time around the loop, antecedent of R will be the previous condition. And so that's what this notation is just trying to show, so you can have the prefix of the rule and keep adding one more conjunction, one more condition, I should say, one more equality condition to the rule one by one. Okay. But the point here is that you're still looking for the attribute value pair that has the maximum accuracy. Okay. Okay, so in this case we started from an empty rule and we incrementally added constraints until we started incorrectly classifying some negative examples. But you can do it both ways. So there's a couple different strategies here. One is to go from general to specific as we just did, which is start with the empty rule and add constraints to eliminate negative examples and stop only when all you have left are positives. But you could also imagine going specific to general, which is starting with a particular instance and constructing a rule that exactly specifies that particular instance, right? So it has a constraint for every attribute and uniquely describes that one data point. And then you could remove conditions one by one in order to try to cover more positive examples, and stop whenever you hit one that covers some negative examples. Okay, and then you move on to the next rule. Okay, so once you have these sets of rules, you need to use them to make predictions. And one thing that can happen is you can have more than one rule triggered for a particular data point, and so you need to have some way of resolving conflicts. So here you might choose the most specific rule, or you might even choose the most general rule, or you could apply some domain knowledge in order to assign a priority to each rule and use that to, break ties. All right. So a recap of this brief introduction to sort of rule-based methods is the representation here is a set of these if-then rules with varying numbers of conditions. Okay. And the evaluation strategy is to come up with the coverage of a rule and measure the accuracy by the number of correct predictions it makes divided by that coverage. And then the optimization is the search strategy is to sort of build rules by finding conditions that maximize accuracy one step at a time. And there you can either go from general to specific or to specific to general. And we didn't discuss sort of the various trade-offs among those choices. And so the maybe takeaway for these rule-based methods, besides using it to build into the next segment, is that one rule or just a few rules is pretty straightforward and pretty easy to interpret. A big set of rules may not be, right? The overall properties of a big pile of rules is not immediately obvious. Okay, so again, we can consider how far we can go with these sets of rules, and we showed that one big flat list that gets pretty complex might be hard to interpret. So one thing we might do is consider grouping redundant conditions, right? And so this starts to look like a program you might write in any language, where you say if the passenger's in first class, then if they're female, then survive equals yes, and if they're male and age less than 5, then survive equals yes or no or whatever. And if they're in second class, then have another nested set of conditions and so on. And so this starts to look like a tree, and these decision trees are what we're going to talk about next. All right. So how this looks maybe diagrammatically is this, right? You sort of drop each passenger down the tree, and each node in the tree makes a decision about where they go based on their attributes, and eventually you end up at a particular bucket. Okay. And so you can imagine here that which attributes you start with on top allows you to generate a lot of different kinds of trees, and they'll have different properties. Now, the relationship between one of these decision trees and the sets of rules is that every path from the root represents one rule. Okay, so you can always turning a tree into a set of rules is pretty trivial, because you just draw a line from the path to the root, draw a path from the root to the leaf, And every time you can do that, you end up generating one rule. Going the other direction is not necessarily straightforward because there's redundant subtrees and so on. So you need to make some decisions about how to handle that. All right. So switching examples for a second, consider going back to this document classification example. You can build decision trees in this case as well. You can say, look, if the document includes the term Sunday, you either have yes or no. And if it includes the word saints, then you have yes or no. And if it does, then it's probably talking about sports, right? And if it includes the word Sunday, but it includes the word Mars, then it's probably talking about science. Okay. And so here, Sunday, the include Sunday yes or no condition being at the top maybe wasn't all that helpful, and we'll make that notion more precise in a moment. Okay, so in order to make a decision about whether a node in the decision tree is helpful or not, which I just claimed that we had an example where one wasn't helpful, we need this notion of entropy. Okay, and a way to think about this is consider two different sequences of coin flips. Okay, and we want to figure out how much information do we get after flipping the coin in each sequence once. All right. So the reason I'm talking about two different sequences is we want to have some kind of relationship between these two different coin flips. And so what we want to be true is that the probability of it coming up heads on the one hand and the probability of coming up heads on the other hand, with these two coins, we know that if those events are independent, which we assume they are, assuming everything's fair about these coins, then you can multiply those probabilities together. And so if we're trying to make up some new function called information, then we want information applied to the joint probability of those two events to be the same as the information gained from one of the events plus the information gained from the other event. Okay. So let me just say that again. We're doing an experiment with two different coins simultaneously, and we're trying to design a function that captures our intuition about what information is. Okay. And it must have this property, right? Any sensible definition of this information function must have the property that if I have two different separate events, I should be able to add their information together to get my total. And that should be the same value as applying the information function to the probability that they both happened. Okay, so with a fair coin flip, it's 0.5 times 0.5. So information of 0.25 ought to be the same as information of 0.5 plus the information of 0.5. Okay, and it's here on the slide. The function that gives you that is log base 2. Okay. Fine, so that's the information. Now what's entropy? Well, entropy measures the amount of unpredictability in a set of events, a sequence of events. And so this is the expected value of the information. Okay, and expected value, whenever you see expected value, you should always be thinking about, I'm going to be multiplying a probability by a value gained if that event occurs. Okay, and so here you're saying, and then adding up all those eventualities. So that's all, expected value in every circumstance is going to be multiplying probabilities by values. And so here is no different. So we take, I pause because I see that there's a bug on this slide, which is, this is negative. Because log of a probability is less than 1, so that's always going to produce a negative number. And we want information to be a positive number, so we need to reverse the sign. And it's reflected down here, but it wasn't reflected in that definition. Okay, so we understand why information is the log function, and we understand that we want the expected value from a whole sequence of events. And so the formula falls out of it. It's the probability multiplied by the log of that same probability, and then add all those up. Okay, and so this guy comes up a lot. We're going to use it in one particular way, but you should keep your eye out for it. Whenever you see, some values from 0 to 1 multiplied by the logarithm of that same value, you're talking about entropy. So let's look at an example. So assume you're flipping a coin, and we see the same expression here on this slide that we saw on the last slide, except that this should say x instead of I. X or I is fine. It doesn't make any difference, but they should be the same. then you expand this expression this way. If it's a fair coin, then you have 0.5 times the log of 0.5 plus 0.5 times the log of 0.5. This representing heads and this representing tails. Okay. And if you compute that, the answer is 1. And this is appropriate because we imagine that flipping a coin gives us exactly 1 bit of information. Right? It tells us the result of one 50-50 choice. Okay, so things are either on or they're off, and when you tell me the answer, I've learned 1 bit of information. All right, so now consider if we're rolling a die, there are 6 outcomes, each having a probability of 1/6. And so use the same expression, 1/6 times the log of 1/6, and add all those up, which is just multiplied by 6 in this case, and you get entropy of 2.58. Okay, so what this says is that when I roll a die and get the answer, I've learned more information. This is less predictable, more unpredictable, right? It's a higher number, more unpredictable than flipping a coin, which agrees with our intuition. All right. So now imagine rolling a weighted die that had these probabilities. You know, values 1 through 5 were all 10% chance, and it had a 50% chance of rolling a 6 every time. Well, we can do the same thing, and there's that bug again. This could be x. So this is 10% times the log of 10% times 5 plus 0.5 log 0.5. And so here you get 2.16. So here a weighted die is, goodness, less unpredictable than a fair die, right? Which again agrees with our intuition, right? Because if you had to bet what was going to come up, you would bet on that a 6 would be rolled. Okay. So how do you apply entropy to a data set as opposed to a random variable? Well, you can do it with respect to the class labels. So if you have 891 passengers in the Titanic data set and 342 of them survived, then you can compute entropy from those two sets. So 342 over 891 log 342 over 891 plus 549 over 891 and so on gives you an entropy of 0.96. So this is almost 1 bit of information. And this makes sense because 342 is about half of 891, right? So it's about, you learned a lot by identifying someone as having lived or died, okay? But then say there were only 50 survivors. Well, then the data set is inherently more predictable, right? Because most people did not survive, and that's reflected in this calculation. You get an entropy value of 0.31, so it's inherently less unpredictable or more predictable. Okay. So fine. So that's entropy. Going back to decision trees. Now, which attribute do we want to choose at each level? Right? We're gonna build a tree, and we have to make a choice of which attribute we're going to use to split on. Okay, and the one we're going to pick is the one with the highest information gain, and we're going to use entropy to compute information gain. And another way of saying that is the one that reduces the unpredictability the most. Okay, so how do we compute this information gain, and how do we use it to make decisions in building the decision tree? All right. So let's go back to this simpler example of predicting when we're going to play golf or do some other outdoor activity. Okay. So before we've made any decision about the decision tree, we've got 14 records and 9 of which are labeled yes. They're positive examples. And so we can compute the unpredictability, the entropy of this data set, just as we have with the Titanic data set and with the die rolls and so on, and we get 0.94. Now, if we choose the outlook attribute to be the root of our tree or to be the next node in the tree, then we see that we'll have 4 records that are overcast, that represent overcast, right? If we choose the attribute outlook, then the value overcast has 4 records, all of which are yes. And so the entropy of that choice is going to be 0. Okay, it's 100% predictable, right? It's 0 unpredictability. All right. And the value rainy has 2 no's and 3 yeses. Okay, so 5 records total. 3 out of 5 log 2, 3 out of 5 plus 2 over 5 log 2, 2 over 5 is 0.97. Okay, and then finally, if it's sunny, then you have 3 no's and 2 yeses, and it's the same value, 0.97. Okay, and so now the expected new entropy, if we have chosen outlook, you compute an expected value. Expected value is the probability of making that choice times the value of that choice. And so 4 out of 14 has a value of 0. 5 out of 14 has a value of 0.97, and 5 out of 14 has 0.97 again, right? And so compute the total there, and it's 0.69. Now, the gain here is the difference between where we started and where we end up. All right, so considering temperature, well, here we have 4 records. Sorry, for the value cool, we have 4 records. 1, 2, 3, 4. And we have yes, yes, no, and yes. And so 3 of them are yes out of 4. And you can compute the formula and you get 0.81. And you can do the same thing for rainy. Oh, excuse me. Should be hot, and this should be mild. All right, and so you compute the same values here. And so with this one, so with hot, we have exactly 2 records are yes out of 4, and so that's 50-50. And remember, that's always unpredictability of 1. Okay. And then finally, when it's mild, there's 6 records, 4 yes, and we get an unpredictability of 0.92. And so then you plug in the formula, and the expected new entropy is 0.91. Okay. And so the gain here is less than it was for outlook. And finally, next we can consider humidity, and here there's only 2 values. 7 records have normal humidity, and 6 of those are yes, and so the entropy is 0.59 if you plug in the numbers. And if humidity is high, there's 7 records there as well, and only 2 of them are yes, and the entropy here is 0.86. And so the expected new entropy here is 0.725. And finally, windy, there's also only 2 values here. So if it is windy, there's 8 records with windy, 6 of which indicate we played, and the entropy is 0.81. And when it's not windy, there are 5 records, 3 of which we played, and the value is 0.97. And run through the numbers, and you get 0.87. Okay, so now we have a computation for every possible choice of attribute, and we compute these 4 gains. And it's really just the minimum of them, since we're subtracting the same amount, same value every time. And so outlook, the first one we did, is indeed the one with the highest gain, and so that's the one we'll pick. And so this sort of makes sense if you think about it. We went through the calculations here just to sort of try to help you internalize what's going on with entropy, but it does sort of make sense. It's the one that, if you can choose an attribute that tells you exactly what's going on, you want to pick that one. Right, so if you always play when it's sunny, right, that attribute tells you a lot of information by selecting that. So you want that one at the top. You want the most discriminative choices at the top. Okay, and just like we showed with that document classification example, we put, well, if the document includes the word Sunday, then we go over here and then we check and see if there's a sports team reference in it and determine the sports. And over here we we'll choose if something related to science is in it. So really, it wasn't much use to pick Sunday at the top. And in fact, I guess I have that on the next slide here. So which of these two has the higher information gain, right? If you include the word falcons, well, falcons might appear in some science articles, and they also appear in some sports articles. And so let's say that down the tree, about half are sports and about half are science on both branches. Okay. But if it includes the word Mars, it's not too likely to be about sports, and so only about 2% of the articles that include the word Mars will be about sports, while 95% will be about science. Let's make sure that adds up to 100. Okay. Fine. So which one of these has the higher information gain? Well, it includes Mars, and so that one would be chosen first. All right. Fine. So what's the algorithm here? Okay, so to summarize this algorithm, which is called the ID3 algorithm, assume all attributes are discrete, and we can discretize continuous attributes by binning them in particular intervals. And I'll give you a method to do that in a few slides. And then you're going to choose the attribute with the highest information gain and create branches, one for each value of the attribute. And then partition the examples based on the selected attributes so far, and you repeat with the remaining attributes on the remaining set of examples. Okay, and so you sort of recursively apply this. And then the stopping conditions are, well, when there's no more examples left, or all the examples along a branch are assigned the same label, because there's no more decisions to make at that point. Okay, and so this in this way you can apply this algorithm and build up a decision tree on your data set. And as you can see, this isn't too hard to implement. The maybe trickiest thing, if you're not familiar with it, is this notion of information gain, which we went through. But other than that, I hope you can imagine trying to write a program that would do this. There's a little bit of bookkeeping to do about building up this data structure, but it's not too complicated. All right. Okay, so what are some problems with this decision tree algorithm? Well, one is that it's expensive to train. You have to sort of keep inspecting these big chunks of the data set when you make every decision. And it's also prone to overfitting, which we haven't drilled into, but this is, in general, what overfitting means is you do really, really well on your training data, but you do poorly on test data, which is to say that the model doesn't generalize. Okay. And so you can imagine that you get these decision trees that are very, very good at making very precise decisions about the training set, but you give it one new example that it hasn't seen before, and it puts it into some bucket that may or may not be right. Okay. And so there's ways around this. You can try to prune branches of the tree that are over-specialized to particular conditions. Okay. And so remove or aggregate subtrees that don't provide much discriminatory power. But there's another way that we're going to talk about in the next segment that's very, very powerful. Okay. Okay, so before we do that, let's talk about how to split continuous attributes to make a decision with a reasonable number of branches, right? So one thing is you could split on every unique value, but given that a measurement value is a floating point number, it's unlikely for there to be too much grouping, in which case you'll have an individual branch for every possible value in the data set, every possible record in the data set, which gives you no information gain, or sorry, gives you a lot of information gain, but doesn't actually help that much. It sort of instantly overfits. Okay, so you want to sort of bucket these things. So how can you do this? So imagine with this weather data set, instead of having humidity labels of normal and high, we actually had the percent humidity as a number. Okay, and so one way to bucket this might be that we're going to say between 60 and 70 is one bucket, and between 70 and 80 is another bucket, and so on. But that requires some domain knowledge, and it ends up being sort of an extra decision you have to make when you're modeling this data. And we're trying to avoid decisions when we're applying these machine learning techniques. We don't want parameters in the system unless we have to. Okay, so what's a way to do this sort of algorithmically? Well, you can imagine that if we sort the data set in increasing order of humidity, pointing to the wrong screen, that every point in this humidity data set represents a possible place to split it into two choices, high and low. Okay, and so what we can do is just evaluate each one of those choices and measure the information gain and choose the point which gives us the highest information gain. Okay. And so here's what that might look like. I haven't actually checked every single one, but I sort of eyeballed it and saw that, wow, you know, the first several have solid yeses all the way up to here. So this might be a pretty good candidate to split on, because on one branch we know we're going to have nothing but yeses, and that's what we're looking for here. We're looking for reducing unpredictability, right? Information gain. Okay, and another good place to split perhaps is down here, because there's a lot of yeses, all but one above it, and no's above this, which sort of makes sense, because as the humidity goes up, we have we're less likely to play outside. Okay. So fine. So if you go ahead and compute the entropy here, here is 6 out of 6 are all yes, which means it's 0 entropy, totally predictable. And here it's 3 out of 8 plus 5 out of 8 entropy is 0.95. And here 9 out of 10 or 1 out of 10, that means it's a lower number, as we'd expect, because it's pretty predictable, right? 90% chance of being a yes. And here 4 out of 4 is 0. Okay, and so now you do the expectation and say 8 out of 14 cases times 0.95 plus 6 out of 14 cases of 0 is a pretty low number, 0.54, but over here it's an even lower number, and so the right place to split is here. And I didn't check the others, but clearly these are the only places that will matter, because it didn't change in between there, which actually suggests an optimization. Okay, so again, we consider every possible binary partition and choose a partition with the highest gain as a way to turn any continuous variable into a discrete variable, so that you can work on this. And you could actually do this more with, instead of just true false, or instead of just high low, you could also pick more buckets to have an even higher fan out. Okay, so where are we? We're talking about supervised learning, and we're talking specifically about classification problems where we predict a class label based on the other attributes. And so we gave an example of predicting whether or not we play some sport based on a few different attributes representing the weather, or predicting whether a passenger aboard the Titanic did or did not survive based on things like their gender, their age, the fare they paid, and so on. Okay, and so to get started here, we talked about just, manually guessing simple rules that might explain the data. And as you might imagine, the relationships between the attributes and the class label are complex, and so, your intuition may be wrong. And so you need some way to automate the search for these kinds of rules. Okay. So we talked about this one rule algorithm that will proceduralize the process of choosing a good rule, and that worked fine. But obviously it's pretty limited, right? It can only find very simple kinds of relationships. And so we also talked about a sequential cover algorithm that builds up sets of rules that may have multiple conditions in them. Okay, so great. So a set of rules that are themselves complex are more descriptive of the data, and therefore have better strength as a classifier, but they're also harder to interpret. And one of the points that we've been making in this class is that communicability of these models, communicability of the results is important. Okay, and so a single rule is easy, a set of complex rules is perhaps less so, and for that reason and for other reasons, we can talk about decision trees. And we sort of showed that a decision tree, I was about to say, can be constructed from a set of rules. Each path from the root is a rule, but that's not quite true. Constructing a decision tree from a set of rules is not necessarily trivial. Going the other direction is straightforward, as we described. Every path from the root is a rule. Okay, but there is a relationship. Moreover, given a decision tree, it's pretty easy to interpret, I would claim, right? You just sort of take your data item and look at the root node and answer the question. Is the gender male or female? Female will then go down this branch, male go down this branch. So it's very easy to understand what's going on. It's also easy to understand what the most important decisions are because they bubble up to the top. Okay. And so if someone's asking you, well, why, how is your model behaving? Why does it make one decision over another? You can sort of answer those questions. Okay. And so we talked about using how you make the decision of which attributes to select at each level, and we talked about entropy being a measure of sort of the purity, right? The game is to try to make an entire branch pure with respect to a class label, right? Everyone down this branch survived. Okay. And so entropy gave us a way to do that. And then we talked about a few extensions for numeric attributes where you could split based on at a particular level, as opposed to, so if you don't have gender, male and female, but rather you have a number like humidity or the fare they paid, you have to be a little more careful. You don't want to have 1,000 different branches coming out of a node, one for each unique value. Rather, you want to bucket them somehow. And so what's the way to bucket them? Well, one idea is just to find a split point that splits into two children. So everything below this value goes one way and everything above this value goes another way. And we talked about how to find that threshold. Okay, so fine. So where we are now is that decision trees are potentially prone to overfitting. And so let's talk about that. This excerpt is from Pedro Domingo's 2012 CACM paper that we've mentioned before. So, what if the knowledge and data we have are not sufficient to completely determine the correct classifier? So it could be that we've, designed a classifier that is responding to what, he calls random quirks in the data as opposed to sort of uncovering some kind of fundamental truth. It doesn't have any predictive power in the real world. It just sort of describes this particular data set. And so the problem here is overfitting. And, he says it's the bugbear of machine learning. A lot of machine learning problems really reduce to how do we avoid overfitting, right? Because you can always train a model on a particular data set, but how do you avoid specializing it to this data set and making sure it has some predictive power in the real world? Okay, and so the case to look out for here is when your learner outputs a classifier that is 100% accurate on the training data but only 50% accurate on test data, when in fact it could have output one that is 75% accurate on both, it has overfit. Okay, and so I want to call out that this is really the definition to think of when you think about overfitting. Low error on training data and high error on test data. Okay. So an image that sometimes is called to mind when you're talking about overfitting is this one, which is, I've fit two polynomials to a small set of data points, one with a high degree, I think 10, and the other with a low degree. In this case, actually it's still pretty high, it's 5. And you can sort of see that a couple things. One is that the red curve is exactly matching the data, okay? But you can also see that the sort of what appears to be the trend in the data probably is better described by the green line. And in fact, it was generated by a model that's sort of adding some random noise to a curve, and so the green one probably does actually reflect the actual underlying data model, the underlying process which generated the data. But the other point to look out for here is it's sensitive to changes, to perturbations in the data. If I move one of these points, just one of these points a little bit, how much does that curve change? And the green one would not change much, while the red one might. Okay, but I actually don't think this curve fitting model is the best image to call up when you think about overfitting, because it's in my mind it's a little bit specific to polynomial curves and the number of degrees of freedom you're working with. Okay, so it's not always clear, at least to me, how to map this image that I call up in my head of overfitting to machine learning problems. So I think a more useful one is one that's actually associated with a Wikipedia page on an article related to overfitting that's released under Creative Commons, is this, that over time your error goes down for both your training set and your test set, but at some point it continues to go down for your training set. I'm pointing at the wrong screen. This continues to go down on your training set, but then it starts to creep up on your test set. And so at this point, he's put a little symbol here to indicate that's where overfitting has set in. And so I think this is the image you should call to mind when you're thinking about overfitting problems, is this difference between the error on your training set and the error on a test set. Now, in some cases it's tough because the test set, may be what is the test set? Is it something you actually have your hands on where you can measure this error, or is it more like the predictive power in the real world? But regardless, any kind of estimate you have over the error that you're actually achieving on data that you didn't train on is what to look out for. And when these start to diverge, that means you overfit. All right. So, other language to be familiar with around this concept, is the model able to generalize? That's when you're if it is able to generalize, then you are not overfit. Okay. Can it deal with unseen data, or does it overfit the data? Test on. So in order to solve for this, you test on holdout data. Okay. So one way to do this is split the data to be modeled into training and test set, just in a fixed way. Train the model in the training set, evaluate the model in the training set, and then evaluate the model in the test set. And the difference between those two, again, is a measure of the ability of the model's ability to generalize. A measure of how overfit it is. Okay. Now, doing this just once, splitting between training and test, is not the most powerful mechanism to do this, and in a couple of slides give you a better one. All right. So another image to kind of call to mind when you're thinking about overfitting also comes from Pedro Domingo's paper, which is this distinction between bias and variance. So in the underfit case, right, you're missing the mark. You're not describing the data very well, but you might have low variance. You're clearly missing the mark. And then high bias and high variance, well, then you're sort of just way off the mark. You haven't, your learner is not producing anything useful at all. But in the overfit case, you might have very, very low bias, but you have high variance. Now, the way to interpret this language I'm using, the high variance, is variance when you add more data, or when you perturb the data, or when you evaluate on a different data set. What's your quality look like? Right? How well do you do? Okay. And so if you have low bias on your test set, but it's sensitive to the data, right? That's where the high variance comes from. Then you're in an overfit scenario. Okay. And in the other case, well, you're not very sensitive to the data. You have low variance, right? But you're biased. But you have high bias. You're wrong. You're getting the wrong answer. So this is like if I just have a model that's always predicting, let's say I have a model that says for the Titanic data set that everybody dies all the time. Well, this is very insensitive to the data, right? It has low variance, right? No matter what data set I give it, it always produces the same answer, but it has high bias. It's wrong, right? The error is high. While overfitting is the other way around. Maybe I'd get an exact answer on my training set where I have very, very low bias, but as soon as I add one more data point, it changes drastically. Okay, so this is another set of terms and kind of concepts to think about when you think about overfitting. All right. Okay, so we talked about overfitting, but backing up a step, we need to talk about evaluating a model and seeing how good it is. So we've touched on this when we talked about rules, we touched on this when we talked about decision trees, but I want to go over the main terms you need to be familiar with. Okay, so maybe the most important thing to take away from this entire segment is about dividing your data into training sets and test sets. And so when you work on Kaggle, you'll be given a training set and a test set, but you should take the training set and split it again. Okay, so this may seem somewhat obvious that you can't evaluate on the same data that you're training on, because of course you'll do well, but this actually wasn't all that clear to people when they were first exploring some of these machine learning approaches in the 80s. It actually took a little while to sort of align what the statisticians already would have realized with the sort of algorithmic approach that the machine learning crowd was exploring. Okay, so this is absolutely critical, right? It means it's meaningless to evaluate a model on the same data you trained it on. Absolutely meaningless. Okay, so how can you do this? Well, one way is to just set aside a certain amount of data, a certain percentage as the test data, and leave it at that, and then do all your training on the training data. But a somewhat more aggressive way is to do cross-validation, which is leave out a certain amount for testing, but then repeat that, right? Leave out a different, do another random sample, and evaluate on that. Okay, so say tenfold cross-validation would say leave out 10% as test data, train on the remaining 90%, right? Evaluate on the set-aside data, and then repeat. Now, k-fold tends to mean that you're going to split this into chunks ahead of time, as opposed to actually doing a random sample in each case. But both are valid, and they have somewhat different properties. Okay, and we're not going to go into a lot of detail on this. Okay. So, and 10% is a reasonable number to think about. A special case of this method is leave one out cross-validation, which is take a single element from your data set, set it aside, train on the remaining records, the remaining data, and then evaluate on that one set-aside data point to see if you classify it correctly. Now, repeat that on every single data item in the set, and you'll have a pretty good idea of how well you're doing overall. Okay. Right. And this also has some properties, both good and bad, that we're not going to go into a lot of detail. And then finally, a related concept that I do want to go into a little bit of detail on in a bit is the bootstrap, where you take a data set and you resample from it with replacement. So you may generate duplicates. And this has some very nice properties for statistical analysis in general. So any statistic you derive from this bootstrap set of samples turns out to be a very good estimator of the actual population statistic. Okay, and so we'll go into that detail in a little bit. Now, I want to have one slide on this leave one out cross-validation, just because I want to make a point about where this came up previously in this course. So again, for each training example, XY, where Y is the class label, and X is a set of all the other attributes, right? We just sort of lump them together and assume for notation purposes. Train a classifier with all the training data except this one particular value XI, and then test the classifier's accuracy on XI. Does it get it right or does it get it wrong? Okay. And then the leave one out cross-validation accuracy is the average of all the other, of your performance on all the set-aside data. Okay, and so the place we saw this before was in the Twitter assignment, where one of the recommendations to debug and evaluate your term sentiment model, not the tweet sentiment model, but the term sentiment model, was to take one of the terms out of the afin.txt file and see what sentiment your model predicted for that term. And you could broadly just make sure that it was sort of positive when the afin said it was positive and negative when afin said it was negative. Okay, and of course this was sensitive to the exact tweet data set you were working with, but it would be a good way to sort of sanity check and make sure that you're producing the right values. And so one of the challenges, if you remember, was, well, the afin file covered a lot of obviously positive and obviously negative words, and therefore you didn't leave you a lot to test with, right? Because afin was one of the inputs. Well, that's okay using this leave one out cross-validation. It is one of the inputs, but leave something out of the quote training set, even though we didn't think of it as really training a model, but in some sense we were. Leave one out and then see what value you predict for that one that you left out. Okay. And you could do this, you could do a k-fold cross-validation as well by leaving out a whole bunch, but just one maybe was the recommendation that came up in the discussion forums. Okay. Okay, so what we have talked about is just measuring accuracy, and we've mentioned this term confusion matrix before. We showed this when we were looking at the rule-based models. So going into a little more detail here, if you are looking at a two-class model, you've got predicted positive and predicted negative as columns and the true positive and the true negative as the rows. Then you can put the numbers in this matrix, and the blue numbers are what you got correct and the red numbers are what you got incorrect. Okay, and so A is the true values that you predicted to be true, and the D is the true negatives that you predicted to be negative. Okay, and so here accuracy was, well, just add up everything you got correct and divide it by the total. Okay, so this is straightforward. So why not use this all the time? Well, in many cases, this isn't necessarily enough to really tell you anything. So how do you interpret 90% accuracy? Is that good? Is that bad? What is it? Is 99% accuracy really, really good? Well, it depends. It depends on the problem. And so you need some kind of a baseline to compare this with, at least, or you need to use a different measure. So possible baselines here is a base rate, and you can define this by just trivially predicting the most frequent class. So for example, in the Titanic data set, this would be everybody survived, or everybody did not survive, depending on which one was more frequent. And I don't actually remember off the top of my head which one was, at least in the trainees that we were looking at. Okay, so take the most frequent class and just assume that that applies to everyone. And that's the one you're trying to beat. Okay. Another baseline is just sort of the random rate, which a lot of times you could sort of assume is 50% for a binary class. But you might actually apply prior knowledge, and so you have a little bit more nuanced probability distribution. For example, if you sort of know that 60% of the passengers didn't survive, you take that as your baseline. Okay. And in some cases, it may even get complicated. If you have some sort of complicated model, you may need to take your prior knowledge and sample from that distribution and so on. But fine. So some sort of randomized baseline. And another one might be a naive baseline that's a little bit less naive than the base rate, and not necessarily random, but uses a little bit of domain knowledge. For example, take some kind of simple default or pre-existing model that you would come up with it without having to apply any kind of sophisticated technique. So for example, all females survived, right? You need some sort of a baseline to compare against, and so you're measuring how well you're doing relative to that. And this comes up actually in the Kaggle competitions because many times you're given a starting point solution. Okay, and so you want to measure accuracy relative to that as opposed to accuracy overall, perhaps. Okay, so there's a few other performance measures that are computable from the confusion matrix, and I just want to flash them up briefly so that they're included in the slides for reference, but I'm not going to spend a lot of time on them. So one is this notion of lift, which you'll see sometimes in the marketing literature. Another is precision and recall, which are concepts borrowed from information retrieval. And the third is the ROC plots, these receiver operator characteristic plots, which is a historical term. And here they are trying to capture these two notions of sensitivity and specificity. Okay, and so sensitivity is the proportion of true examples you got right, and specificity is the proportion of false examples you got right. Okay, one class and the other, survived and not survived. And each test case generates a single point on this curve, but in many cases there will be a threshold that you can set to carve out an entire curve as opposed to a single point. So for example, if you've got a model that says, creatinine levels in the blood determine a diagnosis, well, what should the threshold? How high is too high? How high should the creatinine levels be before you make a certain diagnosis versus the other diagnosis? Okay, and so if you change that threshold, what you'll do is carve out a curve here. And so the point here is that there's perfect is a perfect classifier, is up at this point, right? It gets everything right and makes no mistakes. And a random classifier is this red line in between, and these curves are more often in between these two. Okay, and so you can measure the area under this curve if you want to try to get to a single number. Okay. All right, so we talked about cross-validation to break your data set up into pieces in order to validate your model, and in general splitting things into training sets and test sets, which is crucially important to make any sense whatsoever. But a related notion here is resampling your data set, or maybe a more general notion is to resample your data set. And another use of this is the bootstrap, which is a very, very general and very, very powerful technique coming out of the statistics community in 1979. So here's how it works. Given a data set of size n, you draw in samples from that same data set with replacement to create a new data set. Then repeat this a whole bunch of times. Now what you have is a bunch of different sample data sets drawn from the same population. You can compute whatever statistics you're interested in on each one of these, or you can train a model, which is the context we're talking about. And you can interpret each of these as a sort of individual experiment. And this is exactly what the frequentist perspective calls for, right? If you remember the definition of a confidence interval, it says that under repeated experiments, 95% of the time, this confidence interval will contain the true mean, or the true whatever statistic you're interested in. Okay, and so this is giving you a direct simulation of that interpretation of the statistics. Okay, and so this is a fantastic use of computational resources, right? It means you don't have to sort of have this precise analytic model of the world of what's going on. You can just rerun experiments. And in 1979, this seemed like, wow, this is going to be very computationally intensive, it's not really feasible. Now, for most of these data sets, it's absolutely trivial. And so this is a very, very powerful technique. All right, so here you see an example of this. It's probably pretty clear, but I just want to make sure you see how it works. Imagine that the original data set you're given is just 1, 2, 3, 4, 5, 6. Then you're going to draw multiple samples from this simple data set with replacement. So you might get 4, 3, 4, 2, 1, 6, and you notice 4 came twice, 2, 3, 6, 1, 3, 5, and 3 came twice, and so on. And now for each one of these samples, you can compute the statistic you're interested in, say just the mean. And what you'll get is an unbiased estimate of the true mean. Okay. So great. So that's a pretty trivial case. If you have a more complicated data set like this, and you want to do a slightly more complicated statistic, such as fit a regression line, well, same thing. These are all your points, and you could draw bootstrap samples from them. So this is 100 points, I think. I said 1,000 here. This is just 100 points. Draw 100 samples from this data set with replacement, and then refit a regression line to it. And I've done that here 10 times or so, and you see that the line does wiggle because some of these points were missing. So for example, this outlier up here may have been missing in some of the samples, some of the bootstrap samples, and therefore didn't influence the line, and so it shimmies around. But it stays sort of confined to the data because you're still drawing from the same sample data set. And so by reasoning about how much that wiggles, you can compute things like confidence intervals over these statistics. So if you want a 90% confidence interval for the slope of this regression line, just do this a bunch of times, take the 5th percentile and take the 95th percentile, and you've got it. Okay. So this is really, really general, really, really powerful, associated closely with statistics community as opposed to the algorithmic modeling kind of machine learning community. But we're going to see how to use it for decision trees. Okay. So we talked about resampling, and we talked about the bootstrap, and we talked about cross-validation, where you're splitting your training set into different sets in order to validate your results. So one idea that might occur to you is, well, look, we have all these different subsets of our training set lying around. Why don't we train different classifiers on each one and combine their results, right? So instead of trying to use it to validate one particular classifier, why don't we just make a whole bunch of different classifiers? And so the question that you need to answer is, well, look, can does it actually make sense? Does it work to take a bunch of not very good classifiers and combine them? Will it actually get better? And the answer is not trivial to find out, but it was found out, and the answer is yes. Okay. And so you can average the results of different models, and you get a couple of benefits. One is the strength will go up, the classification performance will be better, and you can drive it up by design. But more importantly, perhaps, is more resilience to noise, and so you reduce the chance of overfitting by having a bunch of different classifiers all work in tandem. Okay, so why wouldn't you do this? Well, there's two reasons. One is it's time consuming, right? Obviously, training a bunch of different classifiers is more expensive than training just one. but also, they become the behavior of your model becomes difficult to explain, right? When you have a whole bunch of different models all sort of voting on the answer, it's difficult to take some intuition for what logic is actually being applied. And so remember we said just like one rule was easier to understand than a big set of rules, one decision tree was easy to understand, a big set of decision trees is perhaps not. But that's not going to stop us from doing it. Okay, so the idea here is that there's this wisdom of the crowds model. Well, it works when you're talking about these digital artifacts as well, these generated models. All right. All right, so how do we actually do this? Well, one technique is called bagging, which is a portmanteau of Bootstrap and aggregating. And so the idea here is to draw your in-Bootstrap samples, retrain the model separately on each sample, just as we described, and then average the results. And so if you're talking about a regression problem that we haven't gone into detail yet on, then you would actually literally just average the results. If it's classification, where you're only picking a discrete class label, then you do a majority vote. Okay, and so this works really, really well for overfit models. It resists overfitting because it decreases variance without changing the bias. So without moving the answer around, right? It just shrinks everything to that answer. And if you remember, we put up that plot where high variance tended to mean overfit. It means that you're specialized to the training data and you're very sensitive to the training data. Okay, but it doesn't help much with models that do have a high bias, with wrong models. And you remember, high bias, low variance models are more or less insensitive to the training data. And so all that you're doing with bagging is taking different permutations of the training data. So if you're not getting a good signal out of the training data at all anyway, this isn't going to help much. Okay. So another technique is boosting, exemplified by this algorithm AdaBoost. Okay, so here, instead of selecting data points randomly with the Bootstrap, you want to favor the misclassified points on each step. All right. So take a Bootstrap sample, retrain a model, see what inspect the mistakes that the classifier made, okay, and recompute the weights for the next round of Bootstrap, giving extra weight to the example data points that your model got wrong. Okay, so let's see what this looks like a little more precisely. Okay, so for each step t, we've got a vector of weights, which represent the probability of selecting example I in the sample. So that's this d. So d at t, d of I, is the probability of selecting I in the sample. And these are initialized to equal probability, to uniform probability. Okay, and then x and y, x sub I and y sub I are your record and your label. Okay, I've been saying data point, example, and record, I think, sort of interchangeably, which probably isn't all that helpful, but bear with me. So h sub t is the trained classifier at step t, using a sample drawn according to the weights d. Okay. Now, compute the error by adding up all the weights for everything that was misclassified, or this epsilon, I shouldn't say error. Compute this epsilon by adding up the weights for everything that was misclassified, and that's what this incantation is down here, right? So this says for the model h sub t, apply it to x sub I, where it's not equal to, where the classifier tells you something different than the actual class label, then include it in the set and add up all the, add up all the d's for those. Okay. Then compute what's called the odds, which is the odds given a probability is that probability over 1 minus that probability. Okay. So compute the odds of misclassifying, and then weight those values, those misclassified values, by the odds. Okay. Oh, excuse me. You're going to that's not quite right. You're going to this is a value between 0 and 1, right? And so this gives lower weight to d of I, and you're only going to apply this function to the ones that were correctly classified. And all the other weights you just leave alone. And so this isn't I didn't put that data for, in an attempt at clarity, I didn't include the entire expression. That may or may not have been a good idea. So this is only applied to the correctly classified examples. Okay, and then there's actually one other step that I also removed in an attempt at clarity, which is you need to normalize all these down, because what you've done now is taken a set of weights that normalize to probabilities. You know, they add up to 1, and you've just adjusted some of them down. Well, now it's not going to add up to 1 anymore. But that's okay because you know the relative weight, so you need to renormalize all this. And so it's a pretty simple step, but I find when you sort of throw a divide by z in here, it gets confusing. So I just wanted to explain it this way. Okay, and then that gives you your new weights for the next round, and then you repeat this process. Okay, so a question I want to ask about this, though, given our appreciation for big data and for scale-out solutions, is the difference between bagging and boosting. Well, I guess I should probably promise you. So boosting has a bunch of nice properties, and it's a very, very successful algorithm. And one thing that's especially cool about this is that it's a meta algorithm, right? It works on anything. It doesn't say anything about what this classifier needs to be. It could be a decision tree, it could be any other method you might come up with, right? All it does is affect the data you use to train the classifier at each step. And so this is very, very general and very, very powerful. Okay. And you know, because of this weighting, it actually does sort of start to zero in on the mistakes that are made, giving more and more weight to the errors. And so you can sort of imagine intuitively that the strength of the classifier is going to get very much better and better over time. So that's well and good, and it works. But it has a disadvantage with respect to really big data relative to a simpler approach, just as bagging. And so that is, it's inherently sequential, right? We have this for each time step, you know, the weights at time t plus 1, at step t plus 1 depend on the weights at step t. With bagging, we can just go wild in parallel and do all of this at the same time. Okay. So that's something to keep in mind that you don't see quite as often in the discussions of these various methods, because they tend to focus on the mathematics involved in the sort of performance. But when we keep in a data science context, we need to keep in mind that we're going to be working on very, very large data sets at times. And so a slightly worse performing but easy to parallelize method can win. All right. So we talked about boosting and bagging and ensemble methods and drawing bootstrap samples. And so some of these ideas we can put together and apply them to decision trees in order to create an ensemble method based on decision trees. And one such ensemble method is random forests, due to Breeman in 2001. And so this one is really, really popular and really, really powerful. Okay, so it's a good one to know. So k times you're going to repeat the following procedure. Okay, where k is a parameter that you'll specify. You'll draw a bootstrap sample from the data set, and then train a decision tree on that bootstrap sample as follows. So until the tree is some maximum size, that is usually set pretty conservatively, you'll choose a leaf node, iterate over all the leaf nodes, and for each leaf node, select m attributes at random out of the p that are available. Okay, so you're not going to use all the, you're not going to consider all the attributes when you're deciding how to split a node. You're just going to select m at random and consider among those. Okay, and then pick the best attribute or split of the attribute as usual, using entropy or other methods, and we'll talk about one more. Okay, so now you have a tree that only involves m of the attributes, and it was derived from only part of the data set. Okay, so now you measure the out-of-bag error. So what's the out-of-bag error? Well, when you draw a bootstrap sample, remember that you might get duplicates, right? So you have a data set of size n, you're going to draw a bootstrap sample also of size n. But whenever you get a duplicate, that means that some other data item was left out of the sample. Okay, so take all those data items that were left out of the sample, and that becomes your test set. All right, so now evaluate the error on that test set, and use this for, you can use this for various purposes. Okay, you don't necessarily need to use it to make decisions as part of the algorithm, but it's computed on the fly as part of the algorithm for various other purposes. Okay. So you can do this to estimate the strength, which is the inverse of the error rate. You can do this to measure the correlation between random trees, right? So each one of these is sort of a different tree using different, potentially different attributes and a different subset of the data. But you can imagine that just by chance you might get a bunch of trees that all do the exact same thing and make all the same decisions, right? This would lower the power, lower the strength of the overall ensemble classifier, and so you don't want that. And so this gives you a running measure of how correlated things are. Okay. And it also gives you a measure of variable importance, which we'll talk about in the next slide. Okay, so finally at the end of this you have k trees that are hopefully more or less independent, and now you can classify data points coming in by just a majority vote among them. All right. So this notion of variable importance. So one of the weaknesses of ensemble methods that we mentioned are perhaps the interpretability of them, right? So a single decision tree makes a lot of sense. If I have a whole set of decision trees all sort of working in concert, it's a little less clear what's going on. And so if you're actually trying to use these models to gain some insight about the domain, that may be difficult with a random forest. All you get is sort of the answers out, and they have high accuracy, but you don't really know why it works. Okay, so variable importance is a hedge against this. So the idea is that you'll, as an output of running this algorithm, you'll get a measure of how important to the accuracy the various attributes were. Or I'm using variable and attribute interchangeably. Okay, so how do you measure this? Well, as you're training each tree, you do this permutation experiment, and we've seen this before, at least I think we have. So you'll scramble the values of that attribute, and what you'd expect is that once you scramble these, the accuracy, the error rate, it may change. Okay, and if it's an important attribute, then it'll change a lot. And if it's not a very important attribute, then it doesn't change very much. And so that's the idea. So if you scramble this and the error rate does not change very much, then it must not have been an attribute that was heavily used in the decision tree. Okay. All right, so you measure the error increase after permuting these values, and you can plot for all the attributes in the data set which ones came out to be most important by aggregating these across all the trees. Okay, and so this helps with interpretability of the overall random forest because you get a sense of which ones are really helping to make all the decisions. All right, and so in some applications, in particular, a few places mentioned that medical applications need to eventually get down to root causes rather than sort of doing fire and forget treatments. All right, fine. So one other difference is the Gini coefficient is often used, and this actually comes up not just in random forest, it comes up in variations on decision tree algorithms. And so we talked about entropy as a measure of impurity when you're making a decision on each node, right? You need to decide which attribute to split on that'll give you the most reduction in uncertainty. Okay, and so you're looking for choices that'll give you very pure choices to the left and very pure choices to the right, right? Where if I select female and male, then I get 100% of the records when I go down the female branch all survive in the Titanic data set. Okay, so somewhere down the decision tree, this may turn out to be the case, in which case that would be a strong indication to use the gender attribute to make the split. Okay, and so we measured this we counted up this measure of intuitive notion of impurity using entropy. Another calculation of the intuitive notion of impurity is the Gini coefficient. Okay, and so this looks like this. And so if you think about what this is doing, right, you can think about how this behaves. We're not necessarily going to derive this, and there's actually varying notions of how to compute the Gini coefficient in general. But if you think about how this is behaving, that if you have probability 0.5, then square that and it'll be plus 0.5 on the other side. Say we have a binary class, so just survived and not survived. Then this will be 0.25 plus 0.25, which is 0.5. Okay. But if you have 0.1 squared plus 0.9 squared, well, that's going to be a lot smaller. Okay. So 1 minus that will be much bigger. Okay. And this makes sense because if 90% of the values are the same, or, you know, if 90% of the values are one value and only 10% of the other, then this attribute is more pure than something that is evenly split. And so you still got this function that's ranging from 0 to 1, capturing some notion of purity. And this has the same properties that has that same property as entropy did. Okay. All right, so now you know both of those methods for measuring this impurity, and you'll see both of them in practice and decision trees and the libraries that implement them. All right, so just a couple of comments about these random forests. You know, one is this is easy to parallelize, right? All that requires is being able to take a random bootstrap sample in parallel, which is usually easy for most data sets. If the data sets are very, very large, it can be expensive to take random samples, but it's still a lot cheaper than training models sequentially. Okay, and so other than that, the training of the trees can all happen in parallel, and so this scales out really, really well. The other nice feature of this is because you're selecting those M attributes at random, where M is oftentimes a lot less than P. You know, you're only selecting a few of the attributes, which makes sense, right? Because if you're going to have a whole bunch of trees vote, well, you're going to make sure that every attribute in the whole data set will be represented enough. You don't necessarily need to have them represented in every single tree. Well, this is nice because it sort of scales to very large numbers of attributes quite well. All right. And then it has these other side effects of being able to generate on-the-fly estimates of its own accuracy and variable importance and so on. Okay. Great. And so just to summarize this, going back to this framework of representation, evaluation, and optimization. You know, the representation here is trees or sets of trees, where the majority vote determines the actual classification. The evaluation of these things has to do with just error rates and accuracy, although we talked about some of the other measures that you might use. And then random forest, we have this out-of-bag error, which is same thing as accuracy, but it's defining where you get the test set from, right? It's leftover. It falls out naturally from the fact that you're taking bootstrap samples. All right, so you don't have to make a separate decision about cross-validation and so on. Although I should say you should still, this is sort of independent of cross-validation. This is, you know, this out-of-bag error is generated on your training set. You should still beforehand, before you even walk up to the table, consider how you're going to do cross-validation or how you're going to split your training set into test and training. All right. And then finally, optimization. It's not so much an optimization as in we have a naive algorithm and we improved it with some optimization, but we do have this information gain Gini index approach to constructively build trees that have good predictive power, right? So we could take, I mean, we say random forest, but it's not truly random in the sense that we're just building random trees, right? Those wouldn't perform very well. We do better than random by making smart decisions about how to split the nodes, which attributes use to split. Okay. Okay, so where are we? We're talking about classification problems and supervised learning. We talked about rules, we talked about decision trees, and then we said a challenge of decision trees is that they are prone to overfitting. And so there's methods for avoiding overfitting in individual decision trees that we didn't really talk about, such as you build them and then you can prune out parts of the tree and aggregate parts of the tree so that they become a little more general. But instead we shifted to another more general and more powerful technique to avoiding overfitting, which is to use ensembles of models. And so within the context of ensembles, we talked about boosting, and in particular, mentioned this algorithm AdaBoost, which is a meta algorithm, meaning that it works on any machine learning application. It doesn't have to be about trees, but we talked about it in the context of trees. Then we talked about bagging, which is about selecting subsets of your data to work on. And bagging itself relies on the bootstrap, which is a technique for resampling the same data set in order to derive estimates of important statistics. Okay, and we put some of that together and talked about random forest, which is an ensemble method for decision trees that has a couple of unique characteristics. Now, I went through this rules and then decision trees and then ensembles approach, sort of sidestepping postponing the regression-oriented machine learning models. And there's a couple reasons for this. One is random forests do turn out to be a pretty powerful method, a pretty general technique for a lot of things. And generality, not just in their statistical power and their sort of efficacy in practice, but also the fact that they work on categorical attributes, the fact that they can handle many attributes, so big P, smaller n cases, the fact that there's different variations of them that you can experiment with, the fact that frankly they're kind of simple to interpret the results of, and also maybe even simple to implement yourself. You know, hopefully you're armed with enough knowledge where you think you could make a go at this. So I think they're actually a pretty fantastic general purpose approach. All right, so let's consider a different method that's not rule or tree based. All right, so that's nearest neighbor classification. So here, this is actually one of the simpler ones, and there's a reason, you know, it'd be reasonable to actually present this first, but the reason I didn't do that is that it assumes only numeric attributes, and I think a lot of the intuitive data sets you work with, especially when you're coming from kind of a you know, maybe data processing background, data science sort of scenario, as opposed to a pure machine learning, pure statistical you know, background, the categorical data is quite common, and so defining nearest neighbor is sometimes possible, but it's not always very natural. Okay, but now that we've sort of covered the more general techniques that can handle categorical data, we can think about these. So nearest neighbor is dead simple, right? This is to say, plot your points in a space like this, where the red squares represent one class and the blue squares represent another. You know, maybe survived or not survived in the Titanic example. And when you have a new point that you want to classify, just drop it into the space at wherever point you know, the attributes tell you where it should go, and choose the class of the nearest point to it. Okay. So what's the class of this green triangle? Well, the closest point to it is a blue circle, so we call it blue. And what's the closest point to this green triangle? Well, that one's a red square, so we call it red. Now, as you can see in the second case, maybe it's not that reasonable to call it red, because perhaps the class boundary is sort of something like this, and this one's, you know, an outlier. This one's a mistake. And so we perhaps would misclassify this second green triangle. All right. So the intuition here is, you know, going back to this sort of document classification example, well, the last document I saw that mentioned the word Falcons and the word Saints was about sports, so I'm just going to go ahead and assume that this document is also about sports since it has the same terms in it. Okay, and so this is not the most unreasonable method to use, but as we saw, you know, perhaps it's a little bit sensitive to noise in the data. And so another, you know, a simple extension of this is to imagine k nearest neighbors as opposed to just one nearest neighbor, right? So you find the k closest points, and then they take a vote on what class it should be. Okay, and this gives you a little more resilience to noise in the data at a cost. So you can ask yourself, how would you choose k? All right, what should k be? Well, the benefits of a small k are that it's fast, and there's less of a bias towards popular labels. And what I mean by that is that if you have imbalance in your data, right, so you have, say, many more people that survived than didn't survive, then there's going to be a lot of those blue circles relative to red squares, let's say, right? And so therefore the odds that you're going to land somewhere near a blue circle assuming a certain amount of noise in the data, goes up. And so you'll start to misclassify more and more and more, as a result. And so imbalance in the data translates into higher error rates. However, the benefit of large K, even though it's sensitive to imbalance, is that it ignores outliers, right? You're insensitive to the outlier. So choosing a K is perhaps problem specific, and there's been work on making this more precise. Okay, so the other decision you need to make is some kind of a similarity function. And so typically you would imagine just Euclidean distance in these cases. But another one that might make sense is cosine similarity, which is a measure of the angle between the two vectors. So if you have 2 points in space, this line D is the distance between them, while the cosine similarity is how far apart they are in the angle. So you have to think a little bit about what the trade-offs are here. So if I was in the classroom, I would ask you guys, I would wait for some answers, but since I'm not, I'll pause dramatically and then just talk about it. So one thing to remember in general is when anybody asks what is the problem, what is the disadvantage of Euclidean distance, you should always have the same answer in mind, right? There's one big disadvantage of Euclidean distance, and that is that it's sensitive to the number of dimensions. So as the number of dimensions goes up, the distance between points is sort of hard to interpret, right? Because it tends to go up as well for not necessarily any kind of good reason. And remember that a lot of these machine learning applications will have a very large number of dimensions, right? So all the English words, for example, in the document classification case, all right? So that's fine. That's the disadvantage of Euclidean, is that you have this sort of curse of dimensionality problem going on. The disadvantage of cosine is that it kind of favors the dominant components, meaning that if two vectors are the same in all dimensions except for one where that value is much higher on one vector than the other, then the cosine similarity is affected less by that than the Euclidean distance. I should try to draw this real quick. So if I've got a point here and here, and then I've got a red point here and way up here, then the angle to the blue is that, while the angle to the red is that. And so this distance is relatively less sensitive to this increase than Euclidean distance, where this point and this point are much further apart, are sort of linearly far apart. Okay, so what this translates into is that you'll tend to be more similar to neighbors who have a very large value in some dimension. Okay. And that can be a good thing or a bad thing. So in one paper they talk about sort of this being a good thing for image retrieval, because if you have very striking features in terms of, say, color composition of the image. So this is like, you've got a query image and you're trying to look for other similar images, and you extract a bunch of features from the image and you try to find similar ones, and then you want the K nearest neighbors. Then say you have very strong red and brown or red and blue kind of colors in your image, then you're going to find things that have red and blue but perhaps less extreme. Right. Okay. So lower magnitude but still red and blue is should be a returned in the results, while close in magnitude but in a different dimension. So about the same magnitude intensity, but in green and yellow, is perhaps less similar in that application. But this is all very application dependent. Okay, so one final point I want to make about this is this notion of Euclidean distance and its sensitivity to the number of dimensions. So this is random data normally distributed with some variance of, I don't know, 2 or 1 or something like that. I guess a little more than that, probably more like 4 or 5. And just taking 2 points in a d-dimensional space where d is going from 0 to 1,000. So give me a random point in a 500-dimensional space, and give me a random point in a 500-dimensional space, and measure their Euclidean distance. Okay, and so you can see the Euclidean distance is sort of going up with respect to the number of dimensions, even though the random distribution from which these points are drawn is the same. And so as the space sort of expands exponentially, things get sort of further and further apart. Okay, and so this may or may not be the effect you want when you're trying to measure similarity in a high dimensional space. All right.